All right, how's it going? Cool. So, any questions? Yeah.
So on the SLP,
Mm-hmm.
the solution specification, and it says a solution block diagram.
If you have a solution and you can write a block diagram for it, you can put it there.
But you don't have to have one?
No, so you want to tailor this kind of to what you're doing, right? So if you're building, you know, a system that automatically opens the door when you walk up next to it, right, your poster is going to look very different from if you're writing a video game, for example, right? So whatever makes sense. If you've gotten to the point where you have some sort of solution, an initial idea, for example, that's a good thing to put on the poster. If a block diagram makes sense, do that. If it's better, just describe it in a paragraph of words or a flow chart or, you know, whatever. Yeah, mix and match as appropriate.
Okay, and then for the competitive analysis,
Mm-hmm.
what is
So we're not actually trying to, you know, come up with a marketable product that's going to shock the market space, but with that mindset, right? So what's your goal here? What's the service you're trying to provide? I'm trying to give students something to do when they're tired of studying, so I'm making a video game. Okay? Competitive analysis would be like, well, you know, there are other video games out there already. So what's my angle? What am I thinking that I'm going to do that, you know, is going to be different from what's out there? Well, my game's going to be free, you know, that's a nice thing. Or, you know, whatever. So it's just kind of, you know, it's nice to sort of think about other things that are trying to do something similar to what you're doing. And you may be doing something that already exists, right? That's totally legitimate. But you're doing it your own way. You're not just making a carbon copy of something that's out there. So think about your approach to whatever your solution is and just try to sort of compare it to what else is out there. So we're trying to get in the mindset of being an entrepreneur, right? Even though, like I say, most people at this stage won't be coming up with something that they'll go ahead and market afterwards, but occasionally people do. I've had students who have like started whole businesses based on their SLP after leaving Clark, so that can happen. All right, any other questions? All right, well, I want to finish our work with balancing trees. So I've got some more sheets up here. Go ahead and break yourselves into groups. Grab a sheet per group. You got to erase the boards this time. And let's just do one or two more balances, picking up from where we left off yesterday. So let me draw a picture of the tree that most people got to yesterday. And so we had inserted the following nodes, and your tree probably looked like this. So go ahead and recalculate the balance factor for each of these nodes and write it in next to it. You need erasers?
Yeah, preferably.
Oh, there's one on the corner of the table there. The erasers are there. So this is the tree you should be starting with.
Right, so this one has. Yeah, right. I don't
Yeah, go ahead and fill in your balance factors. Do you know how to do the balance factor?
make this with right.
So can you write in your balance factors first?
I think it is. I think it was from 3 minus or 2. Is it 1 minus 3? This is maybe the height of this is today.
Alright, now you're good to go.
The first one that is greater than one less than negative one is the one that
So check the balance factor out for you again.
oh.
Good. Okay, yeah.
So I'm thinking of
Alright, so everyone's got balance factors, so figure out which case you're in.
and if it's one greater than one less than negative
I'm just looking at this right here. We are here.
So which adjustment do you need to make first? So is that your first rotation or your second? You get to the
right stack.
that is it. Where's the other one?
Some trees are only different one height. But we need to figure out what sets right in the program.
That's not a binary search tree.
And then do the left, we turn it into a.
So go back to where you've done your first rotation.
Small up.
Yeah, so that makes it another thing and then it bounces down. By making the middle of the left, and then head of that.
so I take it everyone's doing the right left case first. Let me point out a detail here. To do the right left adjustment, you name your nodes, right? The thing that's imbalanced by -2 is node 3, the left child is A, and so on. Make the changes to get to the right case. Keep those same nodes with the same names, okay? So node 3 up here, the original imbalance of -2, that's this node here. That's going to go to the left of node 4 in your final case. So if you label your parts of your tree from this original picture, you can use that to redraw the right case and redraw the balance case. You can actually go directly to the balance case, but go through both steps.
Also, like this. So,
right, we have a 30. Yes.
Cool.
I'm going that way. Oh, I guess.
that way they have the same magnitude of height.
Yes. Exactly.
Oh, that was it.
You figured it out?
I just why like, with what I was like.
I saw that it was a, right.
That's the right answer, as long as you got there the right way, you're good.
These.
Yeah.
Wait, presumably these were the parts of that.
So, right, so that's the right middle one. You lost your 5, but that's okay. Yeah.
So originally, we would have it right like green, and we just make it right like this.
Yeah.
Because it was in balance, so it's not, it's 30, you know? Yeah, 30 being showing off.
30 is bigger than.
Good.
Actually, it's like 40.
Yeah. I have those back.
That's your tree, yeah. Right and left, right? Okay.
Set up like that.
3 and 4 and 5. Right. Right, so you're 22 is hitting up here.
We take the height of the right.
So how does the height of my?
Or you go.
Left tree is -1.
After that. Doesn't actually not after that. It's just in it.
The height of this tree.
That's the 40. Okay. And then 40's left child is going to be the thing that is on the right is 20. So the 30 is on. All right, so I think everybody's got that. So go ahead and sit down. Let's talk through this a little bit, and then we're good to move on. So we've added a node, right? And starting from the node we added, if we work our way up, we find this imbalance right here, the 10. Okay, so we've got an imbalance of -2. Its right child is 1. That's our right-left case, -2 and 1. Okay, here's the way I do these on paper, which people were doing some version of. Let's go ahead and label these nodes and subtrees based on this picture. And I'll put the labels in boxes. So this is node 3. This is the subtree A. This is node 5. Subtree D is over here. This is node 4. And then this is subtree C. And there's nothing to the left of 4, so B is null. So to change that into the right case, we want the new root to be 3, so that's going to be our 10. The left child is still going to be what it was, so that's subtree A. The right child of 3 is going to be node 4. Node 4 is our 20. The left child of 4 is going to be subtree B. Subtree B is null, because that was would have been the left child of 20. So there's nothing on the left of 20. The right child of node 4 is node 5, which is the 40. So that's node 5. And then 40 picks up C on the left, that's the 30. And it retains D on the right, that's the 60. And if we find balance factors, that's 0, 0, 0. At this point we have a -2, a 0, and this is also a -2. Okay, to go from the right case to the balance case, use the same designations that you just came up with. Okay. So the new root should be node 4, that's the 20. The left child should be node 3, that's the 10. It should keep A on the left, and it should pick up B on the right. B is null. And then the right child of node 4 should be node 5, that's the 40. And it keeps children C and D as the subtrees on the left and the right. So it's 30, 60. This is the result of doing the right. Sorry, this was right, left. So the right leaves you with this tree, which is very nicely balanced. So 0, 1, 0, 0, 0, and 0. Okay, so that takes some practice, and it takes working carefully, but you know, it's a pretty straightforward, just move things around, right? If you can actually label these things and keep everything straight, it's just move things around. So I want to look at some code for doing this. And the code will look pretty awful, but it's actually really simple to write. And you can write it almost without really knowing what you're doing. But I seem to have a really hard time finding it. All right, so here's some code for doing this AVL tree adjustment. So first thing I check to do is I check to see if the root is null. And the idea is I'm going to call this every time that I insert or delete a node. And it's possible I just deleted the last node from the tree, and if I try to balance a null tree, all of this will go haywire. So the first thing I check to see is if the root is null, then I don't bother doing anything. I'm just going to return the root, which is null. Okay, otherwise I need to look at these balance factors and figure out if there's an imbalance, and if so, what case I'm in. Okay, so I need a balance factor function that's up here. And it's 2 lines of code, right, like most good functions. If the root's null, the tree is balanced, so its balance factor is 0 at that point. Okay, that's just a definition. Otherwise, the balance factor is the height of the left subtree minus the height of the right subtree. Okay, I need that base case because if the root is null and I try to get root arrow left, I'll seg fault. So that's our definition of balance factor. It's just the difference of the left subtree's height minus the right subtree's height. Okay, so I can call that on a root and find out the balance factor at any point in my tree. So I'm checking to see if I have an imbalance at whatever position root is in my tree. So here's the first statement. If the balance factor of the root is 2 and the balance factor of the left child is -1. Well, if my balance factor is 2 and the left child has a factor of -1, I am in my left-right case. And I need to make an adjustment to change it into this middle case. So I have code called LeftRight that takes the root of a tree, performs that adjustment, and then returns a new root. And then I check to see if the balance factor of the root is still 2. If the balance factor of the root is 2, either I was in the left-left case to start with, and the left subtree had a factor of 1 or 0, or I was in the left-right case where the root had a balance factor of 2 and the left child had a factor of -1, in which case I've just made a left-right adjustment and now I'm in the left-left case. So at this point in my code, if the balance factor of the root is 2, I know I'm in the left-left case. And so the second statement is just if the balance factor of the root is 2, do a left-left adjustment and set the root equal to the new root. 2 more statements for the symmetric situation on the right, and that's the end of our adjustment code. Just return the new root. So this function was really easy to write because it doesn't really do much. It calls these functions left, right, 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 and so on. Those are the ones that do all the work, right? But assuming that I had those functions and I have a balance factor function, if this is a 2 and this is a -1, make a left-right adjustment. And that's what that one line of C code says. Okay? So when I was writing this, I really wasn't thinking about all of this stuff, right? And details like that. I was just saying, if this is a -2, make a right adjustment. Okay? And then you've got your code almost done. You can go off and get lunch and relax and listen to music and then come back later on and say, oh, now I got to write these functions for actually doing these adjustments. And they're not too bad to write. So have some fun, make some ASCII art. So here's what a left-right adjustment does, and this is directly from the Wikipedia page we've been working from. So if the root's a factor of 2 and the left child is a -1, then you're going to change that tree from the top view to the bottom view. Okay, how do I do this? This can be really easy or a real nightmare. Yeah?
This might be the nightmare version. So store everything and then do everything else.
I think that's the nice way to do it.
Oh, okay.
Right? If I have something called node 5 that points to this node and something called node D that points to that node, the root of this subtree, piecing these elements together to make it look like this is just a bunch of assignment statements. And so that's exactly what I do. So here's the left-right adjustment. Okay, that's this case over here. So the root of the tree, that's what we're going to call node 5. Okay, so first of all, I declare some nodes. These are struct node stars, and I initialize them all to null, just to simplify code that you'll see in a minute. And the first thing we do is we say n5 is equal to the root of the tree. Okay, that's this node right here, and we know it's not null because if it's null, we already returned from our adjustment function. So node 5 is the root. Node 5's left child, I'm going to call that node 3, and the right child, I'm going to call that D. So I'm going to say n5, or D equals node 5 right, and n3 equals n5 left. So now I have variables in my program, n5, n3, and d, pointing to those three pieces of my tree. That's a node, and that's the root of the subtree. Okay, I want A to be n3's left child. I gotta be careful here because it's possible n3 is null. And if n3 is null, I can't say A equals n3 left. I'll seg fault. Okay, so just use an if statement. If n3 is not null, set A equal to its left child and set n4 equal to its right child. So I've set up A and I've set up n4. If n3 happens to be null, A is already null because I initialized it in the beginning of this function. Okay, and then n4's left should be B, n4's right should be C, but again, we got to make sure n4 is not null before we can do anything with its left and right children. So if n4 is not null, set B equal to its left child, C equal to its right child. And now we've got names for each of the pieces of our tree. Well, what do we want to do? We're not going to change the root. We're not going to change the root's right child, but the root's left child should become node 4. Node 4's left child should become node 3, and node 3's right child should become B. Since I have variables for all of these things, I can do these in any order I want. These variables have values. They might be null, but I don't need to look at their children, so I'm not going to seg fault. So this is just a bunch of extra assignment statements. So n5 left equals n4. That's building this link right here. n5 right is already D, so that's unchanged. If n4 is not null, set its left child to n3 and its right child to C. So n4, left child is node 3, right child is C. So those are set up. Node 3's left child is already A, so I don't have to do that. All I have to do is set n3's right child to be B. So if n3 is not null, set its right child to be B, and then return the root of that new tree, which is node 5. So set that up and return the root. And that's it. So this code, if you're on the job and someone comes to you and says this code doesn't work, fix it, and they hand you this, it's kind of a nightmare, right? It's no idea what's going on here. Nice lack of comments in there, other than adjust these. But the comments are the ASCII art in the top. If you know what you're trying to do, writing this is, it practically writes itself. Right? It's really just a C version of how you would describe doing this to somebody who is going to do this on the board. Okay, so take node 4 and put that on the left of node 5. And then move C from the right of 4 up to the right of, and so on. And this is very typical of working with data structures. Right? So you want to know what the structure looks like and what the algorithm is that you're trying to do, what the operations are. And then actually writing the code to do those is usually not where the challenge is. It's usually a question of understanding, what do I want to do? Okay, which for AVL trees, some smart people already figured out for us, and some other people posted on Wikipedia, so we just take the algorithm. Or if you have a book on algorithms, right, you get the algorithm from the book. So each of these adjustments is the same way. The left-left case is a little easier because left-left, node 3 doesn't change at all. Node 5 simply picks up C on the left, and node 4 picks up 5, so 5 and C basically swap positions. So that's a pretty simple case. N5 left is C, N4 right is N5, and then just return N4 as the new root. and then a matching pair of mirror functions for the right side. And that's the end of the adjustment code. So I didn't ask you to do this for PA4. I did last year, and that makes it extra challenging. But I wanted to go through this at least in class to let you see this idea of basically mapping an algorithm into code, right? And in practice, you wouldn't be asked to code an AVL tree balancing algorithm, but similar things are things that you've come up with, right? Definitely. So I won't ask you to, like, you know, synthesize this code from thin air on the exam. But I could ask you to take a tree, right, like one of these trees, and tell me what the balance factor is at each point. So know how to do that. I could ask you to look at the balance factors on a tree and tell me what kind of rotation you would perform. And I might ask you to perform a rotation, right? So you want these on your study, your cheat sheets somewhere. And I can always, you know, give you code like this. Like, write some code to change that first thing into the second thing, right? And that's what we've done on, you know, on the midterm, where I had a linked list and I said, you know, write some code to insert a new node between nodes A and B, right? And so you say A next equals new node next equals B, and so on and so forth, right? So being able to manipulate these structures, these nodes, and so on, good stuff to be able to do. All right, so questions on any of that? Yeah. I don't want to print out 45 of them, but if you want to bring it, yeah. I've never actually counted how many pages people have, but but you might want to write a small version of it or something if you need other pages. All right, any other questions? All right. So we're not done with trees, but we're done with trees for now. I want to switch gears and talk about something called dynamic programming, because this is going to be where PA5 comes from on Friday. But we'll come back and we'll talk more about trees. I want to talk about building a stack-based calculator, because that uses a combination of stacks and trees in an interesting way, and it's a nice application. I also want to talk about something called tries, which are really wide trees where each node has a few dozen children typically. And so you can store a lot more information in a shallow tree because your tree gets really wide really quickly. And tries have some interesting characteristics. But we'll come back to those as time permits. I want to switch gears and talk about dynamic programming. And dynamic programming is critically tied into recursion. And so we're going to talk more about recursive solutions. So dynamic programming and recursive solutions. So let me tell you about dynamic programming first of all. So let's think about Fibonacci functions, okay? We haven't talked about these in 215 yet, but we will. But you've probably heard about Fibonacci series anyway. So we can define the nth Fibonacci number is equal to 1 if n equals 0 or 1. Otherwise, it's the sum of the two previous Fibonacci numbers. So we can write down the elements of this series. So the first two Fibonacci numbers are just 1. But the next one is the sum of the first two, which is 2. And then 1 plus 2 is 3. 2 and 3 is 5. 3 and 5 is 8. And we can write down the terms of this series. And so on. And Fibonacci numbers are fascinating things. There's all kinds of symmetries inside that series. And it pops up in nature in all kinds of ways: study of population, growth of sunflowers and pine cones. So it's a cool series. And we can generate it on a computer pretty easily, doing what I just did on paper. All we've got to do is remember what the last two numbers are, add them together, that gives us our next number. And if I just generated 13 and I remember the previous number was 8, I just add those together and I get 21. Okay, so that's an easy function to generate just with a while loop or a for loop. But we can use this definition where the nth Fibonacci number is defined in terms of other Fibonacci numbers. We can use that to write a recursive function by basically just saying, to calculate the nth Fibonacci number, calculate the n minus first, n minus second, add them together. And so that works well. So here's some code that'll do this. So my function at the bottom, fib I, if I is less than or equal to 1, I just return 1. Those are my base cases. Otherwise, calculate fib of I minus 1, I minus 2, add them together, return that. So pretty simple function to write using the recursive definition. And my main program to test this will just call the Fibonacci function for values from 0 through 45 and print out what each of those is equal to. And the first few should match, you know, what we've got here. You have to spell things correctly, though. So we run this, and there's our 1, 1, 2, 3, 5, 8, 13, 21, and so on. But it's not terribly fast. So it just found the 43rd Fibonacci number. It's working on 44. There is 44. And it's got one more to go. And it'll take it a few more seconds, and eventually it'll get there. But this is pretty inefficient, right? This is, 2 billion things a second going on in my laptop. And it took it, 15 seconds to basically add these two numbers together. So sometimes recursion is a really easy way to think about a problem, but it's a pretty inefficient one. And why is this inefficient? Suppose you want to calculate the 5th Fibonacci number. To do it recursively, we need to calculate the 4th and 3rd Fibonacci numbers. To calculate the 4th Fibonacci number, you need to calculate the 3rd and the 2nd. To calculate the 3rd, you need to calculate the 2nd and the 1st. To calculate the 2nd, you need to calculate the 1st and the 0th. And to calculate F1 and F0, we don't have to call the Fibonacci function. Those were our base cases. Those were hardwired. But to do F5, we had to do F4, which required F3 and F2, and F3 required 2 and 1, and so on. And over here, to get F3, we had to do F2 and F1, and to get F2, we had to do F1 and F0. And so to calculate the 5th Fibonacci number, we made 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 calls to the Fibonacci function. And this number of calls is increasing dramatically. To do the 6th Fibonacci number, we're going to have to do all this work to find F5, and then all of this work to find F4. And that whole amount of work that we do to get F6, to do F7, we're going to have to do that whole amount of work again, and then do all of this work for F5. So here's a function where I have a global variable called count. Before I calculate a Fibonacci number, I will set count equal to 0. And then every time I call my Fibonacci function, I'll increment that count. And when I'm done with my initial call to fib, I'll print out the answer and that count. This is just something I've wired in so we can see how many times the Fibonacci function is called to calculate fib of I. And so you can see the number of calls is growing quickly, and it's kind of on par with the value of the Fibonacci function itself.
So gets the best of it.
How long do you think it'll take to get to 1,000?
It will not get to 1,000. If you look at the number of calls compared to the Fibonacci number, what's the relationship?
Is it?
Yeah, it's just about double. It's actually one less than doubled, which sort of makes sense. So we could actually calculate Fibonacci numbers by just counting how many times we have to call the Fibonacci function to calculate the Fibonacci number, and then add 1 and divide by 2. So it's recursive in a lot of ways. This will probably never get to, well, it definitely won't get to 60 in this class, and I doubt it will get to 70 in any time, because it's roughly doubling each time. And I already blew up the size of my integers, so we flipped over to negatives. All right, so why is this so horribly inefficient? Because when we are trying to calculate F5, we had to calculate F4 and F3. We also calculated F3 here to calculate F4. And we calculated F2 a number of spots. And if this takes us, let's just say it takes us a second to generate F5, then when we want to calculate F6, we're going to have to calculate this again. So it's going to take another second, plus however long F4 takes. And if we're trying to calculate F7, it's going to do all of that work again. Right? So we're repeatedly calculating the same values of Fibonacci numbers, and that's what's taking so long. Right? We're making all of these calls to the Fibonacci function, but really to calculate Fib 38, we only need Fib 37 and 36. And to calculate 37, we only need 36 and 35. In fact, if we had the value of all the Fibonacci numbers from 0 through 37, it would take 2 calculations to calculate Fib of 38. So the idea of dynamic programming is if you have an algorithm that has this recursive nature to it, but also this characteristic that you're repeatedly generating the same subcases. In this case, we're repeatedly calculating, say, F3 or F4 or F5. If we can save those results in memory, so that the first time we need that result, we calculate it recursively, but any time after that we need it, we just pull it out of memory, we can speed up our algorithm. So here's the same version of the Fibonacci code, but with this dynamic programming element added. So I have an array I call save. And the idea is when I calculate the nth Fibonacci number, I'm going to save its value in element n of this array. And the only change I make is in the beginning of my function, I check that save array to see if I've saved a value. Now I initialize this to all zeros, and I know my Fibonacci numbers are always bigger than 0. So if the element of that save array is equal to 0, I've never calculated this value before. But if it's different from 0, I must have already calculated this and saved it, so I just return that saved value. And we circumvent all of this. Right? We don't have to do any of that, and that's the recursive part. But if we're trying to calculate fib I and the entry in our save array is still 0, we've never calculated it before. So now we do the recursive work that we've done in the previous version, right? Calculate the 2 smaller fibs, add them together. But then before we return, we'll go ahead and save that answer in our array. Next time we want fib on the same I, this will say, oh, that value's been saved, and it'll just return it. No more recursion. So to wire in dynamic programming, it's really just 2 things you add to your recursive function. In the beginning, check to see if you've calculated this value, and if you have, just return it. Don't do any recursion. Otherwise, at the very end, just before you return your answer, save it in your array. Okay, those 2 changes will make all the difference in the world. So there's our first 1,000 Fibonacci numbers. And we blew up the size of a long int, but, you know, we're well past what we would have gotten to any reasonable time before. And look at the number of calls that it takes to calculate each of these Fibonacci numbers, 3 calls. Because the nature of the Fibonacci series is that in order to calculate F5, we've already calculated F4 and F3. because my main program is calculating these things in sequence. So our first calls, only took one call because they were hardwired as base cases. Then we calculated F2, that took 3 calls, but now F2 was in our save array, and so to calculate F3, we could just read from the save array, and so on with F4 and so on. Now, if we weren't going in order, if, say, I started from 70, then our first calculation takes 139 calls. But then after that, it's very efficient.
Does he have a way to extend the integer size?
Long is as far as you can typically go,
Can you artificially make it?
but you can artificially make it bigger, yeah. So if we run backwards, my first call took 199 calls. But in order to calculate fib 100, I had to calculate fib 99 and 98, which required me to do 97 and 96 and so on. And so after that, all my save array was already generated, and each of these subsequent calls took a single call to fib. And you just read the value out of the array. All right, so PA5 is going to involve a very recursive function related to dropping eggs off of a building. And we're going to talk about some other functions first. We're going to talk about something called the knapsack problem. We'll talk about a rod cutting problem, and a longest sum problem, and then we'll talk about dropping eggs off buildings on Friday, and that'll be PA5. All right, so we'll be playing with this for the next few days, and then sometime next week we'll come back and start talking about other subjects. All right, so see you next time.